Okay, we're talking about fracture, and what I'd like to do now is to take the concept of our fracture criterion and eventually apply it to design and analysis. Now, we're going to be going beyond the types of cases that we have considered so far. We have pretty much considered only one case, actually, more or less, and that was the ideal case, the prototypical case that I'm going to discuss right now once again to remind you. But remember, eventually, the criterion for fracture is always the same, and that is based on the seminal idea of or analysis of Irwin, which says that, well, you calculate a stress intensity factor and compare it against the critical value or the fracture toughness, okay, Kc. Now, we might have noticed multiple modes, but irrespective of the mode, always the same idea will apply. So presently I will write mode 1 because that's what we are going to look at first, but eventually you calculate that quantity compared against the fracture toughness, and it should be less than or equal to. If it's less, you're safe to within a certain safety factor that is given as the ratio of this quantity to that quantity. If it is equal, you are, again, perhaps to within a safety factor, it's the onset of fracture, and it should never be greater than the toughness value, the critical value. So the prototypical case that we have discussed, which I'm going to call the ideal case, remember, it's just a plate with a thickness T. The thickness is irrelevant to the material parameters and eventually the equations that we are going to write. However, it is relevant to the calculation eventually of the stresses because I will eventually apply a load here, and I will need to calculate a stress which scales inversely with T. So now that's the load that we will apply in this case, and as a result of that load, of course, if you like, let me write it in this manner. What we will have is a distributed load across the cross section, provided that I am sufficiently far away from the presence of a crack. Okay, so that crack is actually extending throughout the cross section. Okay. So it's a through thickness crack, that's what we call it, because there are, it turns out, other types of cracks. The crack does not need to penetrate through the whole thickness, it turns out, but presently that's what we are assuming. And the width of this crack is 2a, or half width is a. Now remember, always the half width of the plate is b, and therefore the whole width is 2b. There is actually a height according to our assumption. And one important assumption is that that height is much, much greater than the dimension b. So in other words, if it's sufficiently large, then the far away loading, the far field loading is uniform. And that is what we called so far S. Now, from now on, instead of S, we are going to use the notation SG, and G here stands for the word gross. Okay, so gross to indicate or remind ourselves that this is different from the average stress at the cross section where the crack is present. So first, let us define what SG is. SG is consistent with our very first definition, where we assumed that the crack was very small, or essentially we were looking very far away from the point of the presence of the crack. We said, well, the stress is P divided by the cross-sectional area, which is in this case 2bt, the width times the thickness. That's the area of the cross-section. Okay, so now that is the gross stress, and it is different from the stress that you would calculate, the average stress that you would calculate at the point where at the cross-section where the crack is present. Okay, at that point, the width is reduced by the presence of the crack, and therefore the cross-section area is reduced, so the stress is higher. So this stress is the average stress where the crack is present. Okay, notice that's just an average stress. In reality, the stress in the vicinity of the crack tip is extremely high, and in fact, according to the elasticity assumption right at the tip, we've seen that it's actually infinitely large due to a infinitely large stress concentration. But it rapidly decays away to the gross stress value. The average stress value must be larger because the cross-section area here is reduced by the presence of the crack. Okay, but what we are going to use in our calculations, it turns out, is the gross stress. In other words, when we calculate the stress that is relevant to the determination of whether crack fracture occurs or not, that stress is going to come from a calculation where the area reduction due to crack is omitted. Okay, I'll come back to that once again further. Okay, so now that stress sufficiently far from the crack is uniform if this assumption is satisfied. If it's not satisfied, there will be an edge effect. In other words, no matter how far you cannot move that far from the crack because the height is not that large. So when you actually apply a load of this type, you will never have at any cross section a very uniform loading, very uniform stress distribution in that direction, normal stress, because you can never be sufficiently far away from the crack location. Every point throughout the plate will feel the presence of that crack. Okay, so but presently that's what we are going to assume, and for sure sufficiently far from the crack, the stress will be uniform and looks like that. Okay, now what we have also assumed, and this is a second crucial thing and perhaps the most crucial thing at the beginning, we've also assumed that A is much less than B. The way I'm going to denote it from now on is by defining a ratio alpha, and we are going to say that alpha presently is much less than 1. Okay. Now this definition always holds, but whether or not it's much less than 1, it's something that's going to be debatable. Now, with that in hand, with all of these definitions that I have introduced, and perhaps here on this picture, we have to remember this prototypical picture, and we have to remember the definitions of SG and alpha, and the fact that it's much less than 1. We have to also remember the definition of the mode 1 stress intensity factor, which is simply SG root pi a. And remember, it has units megapascals, square root meters. This is the ideal case. We must know the ideal case. All right, ideal or prototypical. Now, that is the scenario that we're looking at, right? But this is a highly limited scenario. Now, first of all, in this case, the crack is in the middle of the plate and I'm pulling on it. And there is a crack which is right at the center and it's much less than the width of the plate. And the height of the plate is much larger than the width of the plate. Okay. So here's a scenario that we considered earlier, which I just broke a while back. In this case, you see actually that the height of the crack is indeed much larger than the width of the crack. So if I pull on it, right, this assumption will certainly be satisfied. But if you look here, there is certainly one thing that doesn't fit this picture. When I pull on it, the crack, first of all, is not at the center, but at the edge. So it's not a similar scenario. It turns out it certainly is not a similar scenario. We're going to consider it shortly. Two, the width of the crack is probably not very small with respect to the width of the plate itself. Now, is it small or not small enough is going to be something that we will debate always, because how small, the question of how small, is always coming with an answer to within a certain accuracy. We can say small enough according to this or that criterion. We're going to also introduce a measure of smallness very shortly, but probably in this case, the crack is not small enough. It turns out, indeed, it's not small enough. Now, third, I don't need to only pull on this plate. I can also try to bend it, and that's exactly how I broke it, right? I can bend it, right? And notice when I'm bending it, I'm not going to try to close the crack, because in that case, there will be no stress concentration, there's no tension, so there is nothing to consider with respect to fracture. I need to bend it in such a way that I try to open the crack surfaces, move them apart from each other. So when I bend it, it's not tension, so it doesn't also fit that scenario. So even with a simple geometry like this of a plate, I can easily deviate away from this ideal case. The ideal case is still very important, because that is the prototypical case from which we first showed analytically the appearance of K1 in the expressions for the stress fields, how they vary with position away from the crack tip. But it is a very limited case. Plus, the geometry doesn't necessarily need to be in the form of a plate. It can be a, let's say, cylindrical rod, right? And there can be a fractured surface on a portion of it, a crack that is not necessarily of that geometry, etc., etc. So, those are the types of generalizations that we would like to address a little bit. Okay, but in all cases, that will be the criterion. K will be less than or equal to Kc. In this case, we're looking at mode 1. There will be other modes. The geometries of the crack and of the specimen will be different. Okay, so now let's take this first case, put it away, and try to look at generalizations step by step. The first generalization we are going to consider is, well, what if the crack geometry is different? Okay, I'm going to draw 3 pictures here, and I'm going to do all of that in 2D. Just faster to draw. In all cases, just remember that the crack that I'm drawing is a through thickness crack. The crack goes all the way through the thickness T, and it has a rectangular geometry, just like I have depicted in the previous slide. Okay, so that's the plate. And in all cases, I am going to pull on the plate with a load P. Goes without saying, there's a load on the other side. Okay. And now the crack geometries will be different in the following way. In the first case, I'm going to put a crack just like I did earlier of width 2a. Notice I've drawn it quite large for a reason. In the second case, I'm going to put a crack on the left of width a, on the right also of width a. Okay, so still overall width is 2a, but half of it is on the left, half of it is on the right. Here the width is 2b of the plate, here it's also 2b. In this case, we're going to think as though we take a cut through the plate, and we are going to imagine as though there is a crack only on one side of width A, similar exactly to that scenario, okay? And we are going to denote the width of the plate, in this case B. There are exceptions, usually the half width of the structure, sometimes it's the radius is B. Now, in this particular case, it's defined, the whole width is defined to be B. So this is a case where we need to be a little bit careful. We don't have to memorize these cases. On the contrary, just be careful that you don't call something, let's say, the width B, irrespective of what the geometry is. The geometry will influence the definition of what B is. Okay, now, in all cases, SG is defined to be P divided by the area. Okay, now the area of the cross section, but where we omit the presence of the crack. That's the idea of the gross stress. Now, in this case, that area is B times T. Whereas in these two cases, SG is equal to P over 2B times the thickness. Okay, so here the definition of SG is the same as before. Here the definition is the same, and quantity, the way it appears only is slightly different through a thickness, through a factor of 2. Okay, so but the definition is verbally, it's always the same. In fact, this definition that I will now make and write will apply to more complicated loadings. SG is defined as the largest stress. Let's write it over here. SG, maximum stress, obviously in the normal direction in this case. If it's a torsion type loading, it will be the shear stress. It's the maximum stress at the cross section where the crack is present, but omitting the presence of the crack. In other words, omitting the area reduction due to the crack. So here we're looking at the maximum stress at the cross section where the crack is present, but omitting the presence of the crack. So in this case, it's simple. The max stress is the same as the stress at every point, omitting the presence of the crack, because it's going to be uniform stress distribution if I omit the presence of the crack. So it's P over 2BT. Same here. Here, max stress at the location where the crack is present, omitting the presence of the crack. P over B times the thickness, etc. But the definition that I've written in green is going to apply to more complicated loading scenarios. We'll see how that goes in a second. Okay, so now I have not written presently that A is necessarily much less than B, but let us assume that that is the case. A is much, much less than B. And here as well, and here as well. Okay. Now, if that is the case, okay, then it turns out that the definition of K1s, first of all, in this case, is equal to SG root pi A. Okay, that's what we have already written in the previous slide. Now, this case is a different case. It's not the same crack geometry. And because it's not the same crack geometry, it turns out the expression for K1, remember, what does K1 do? It goes into the stress distribution expressions in terms of the radial distance, cosines and sine, thetas, the orientation from the crack tip, etc. We've discussed those expressions because they explain the role of K1. Ultimately, they help us determine whether fracture occurs or not. But we have to remember they are quantities that incorporate all load and crack geometry information, and they eventually determine the stress distributions. They appear in the stress distribution expressions. So that distribution depends on the geometry that we're looking at. In this case, we've already written it. In this case, it turns out that this expression is slightly different, and it takes a factor of 1.12. Okay, so the definition of K1, which goes into the stress distribution expressions, is slightly different. The fracture toughness is almost like a material parameter, so eventually to decide whether fracture occurs or not, I will always be using, as I've written in the previous slide, K1 less than or equal to K1C. So that criterion does not change. This is almost like a material parameter. But K1, the definition of K1 is now changing because the geometry is slightly different. And it turns out in this case, it's also a similar scenario. K1 is equal to 1.12 SG root pi A. Okay, so this is the situation when A is much, much less than B. Now, on the other hand, what happens if A is actually not much, much less than B? So if A is not much less than B, okay, and now I'm going to keep writing on the same slide, then it turns out that K1 is not given through that expression, okay? And instead, K1 is equal to some factor, a function, it turns out f, okay? I'm going to define it just in a second, multiplying SG root pi A. Okay. Now, you may also wish to, I strongly advise so, that you understand and remember this expression for the stress intensity factor. In this case, it's for mode 1, but the expression is going to be the same for any type of loading, any type of load, and it will always be of this form, irrespective of whether the crack is much less than the width, or for that matter, the height of the plate is much greater than the width of the plate. So irrespective of those assumptions, this is the most general expression that we are going to work with. Essentially what this expression is saying, if some of our assumptions are not satisfied regarding the loading conditions or the geometry, size of the crack, etc., this simple expression or these will not hold. So I will replace the factor of, here there's a factor of 1 if you like, here's 1.12, etc. Different conditions have different factors. I'm going to replace those by another factor f, and that factor will help me take into account any possible errors that I'm making. Okay, and I am proposing that now this is an exact expression for K1, to within some uncertainties that probably have to do with the way this f has been determined. But this f, it turns out, is a function of alpha. And remember, alpha is, in all cases, this is true, alpha is the ratio of A to B. Okay, it's a function of alpha, and it is called the form factor, because it sort of takes into account the form of the crack, if you like, and the form of the loading, etc. Now, how does f look like? We can easily draw what it looks like, and it does make sense the way it varies. So this is the value of alpha. Now, the largest value alpha can take, obviously, it's 1. That's when the crack extends through the whole cross-section, right? A is equal to B, essentially. So that's the limit, 1. And here I'm going to write the value of f. Now, f will start at a certain value when alpha is very small, right? And that value depends on, let's call it f of 0. F of 0 is the value of f at alpha equals 0. It depends on the case I'm considering. F of 0, when alpha is much less than 1, so it's essentially 0, it is equal to 1 for that case. It's 1.12 for that case, also 1.12 for that case. It has different values for different cases. Okay, so that's the way we define fracture. But now, what happens if alpha increases? Now, let's try to imagine what should happen. What we're trying to determine is whether fracture occurs or not. If there's a certain load, and if I increase the size of A, eventually it will be so large that as soon as I apply this P, the actual average stress in the vicinity of the crack tip, the average stress, I'm not talking about the point stress at the tip of the crack. If the crack is very large, the average stress where there is material at the cross section of the crack will be extremely large. It will be much larger than the gross stress. Remember, the gross stress omits the presence of the crack. That's a key word. So when the crack is very large, the average stress will be so high that immediately it will lead to the fracture of the material, because the amount of elastic energy that is physically stored in the vicinity of the crack tip is so large that when the crack tries to propagate a little bit, the amount of energy stored is sufficient to keep itself propagating. That's why average stress is conceptually important. It's not important in our expressions, but its importance, the size of the crack, which ultimately, in a sense, influences the average stress, is now going to come through the value of F. So when A is very large, and therefore all alpha approaches 1, for even very small p, in other words, for very small SG, fracture can happen. So P is tiny, SG is tiny, yet K1 can be very close to K1C, which suggests that the way the form factor is going to vary is it's going to start from the value of F at alpha equals 0, so 1 or 1.12 in these cases, and it's going to rapidly increase. And it's actually going to blow up to infinity, because if A is very close to being the width, even a tiny amount of gross stress or a tiny amount of load, which is proportional to SG, is going to immediately cause fracture. So it's going to blow up to infinity. So that's the way F always looks for any type of loading. Now, the exact value of form of F, the form of the form factor, and when I say form, the functional form, the way it depends on alpha, depends on the case we are considering. If I'm pulling with that or that geometry, or if I'm bending, or if I'm torquing, etc., every case has its own alpha. Remember, I assumed that the height of the plate is also very, very large. If it's not sufficiently large, the form of alpha again changes, etc. So the form factor takes into account the deficiencies in every assumption that I have made regarding the crack scenario that I'm considering so far. So that's why it's called this form factor, or compensation factor, if you like. Okay? So now one thing we can look at easily is the following. Now, F is a quantity that directly scales SG root pi A. So if F doubles, the value of K doubles, right? Or triples, the value of K triples. So it's directly proportional. K is proportional to F. Therefore, any possible error in the calculation that I'm making for K is, or can be, attributed to the error that I'm making on F. So for instance, if the value of F for this particular case is supposed to be 1.2, but instead I take it to be 1, then the error I'm making on K1 is 20%. Do you see that? So suppose F is supposed to be, because A is not much less than B, if it is, it should be 1. But if it is not much less than B, suppose it's so large, it's not 1, it's over here, and the value is 1.2, okay? So instead of 1.2, if I take it, and that's the exact value, if I take it to be 1 instead of 1.2, the error on K1 is 1.2 versus 1, 20%. It directly reflects on K1, okay? So one natural thing to ask in this case is the following. What is the, not quite natural, but something that people have agreed on, let's say, what is the 10%, so I'm going to write here 1.1 times F0, 10% error limit on F0, on F, for from the value of alpha at 0. So in other words, I start from alpha equals 0, and I keep increasing alpha. The value of F at 0 is a certain value, let's say 1. And then I keep increasing this value of alpha, and at some point I reach a value of F that is 10% more than the limiting value F of 0. Okay? And let us call that value alpha 0. Okay? So alpha 0 is the value of alpha at which F takes a value that is 10% larger than the value of F at alpha equals 0. Okay? So now, what I'm going to do is, or the way I'm going to make use of this information is as follows. I can say that if alpha is less than or equal to alpha 0, okay? So let me write it here first. So K1 is approximately equal to f of 0 SG root pi a if alpha is less than or equal to alpha 0, and the error I'm making here is 10%. So with 10% accuracy, 10% on f and therefore 10% on k1, I go ahead and look at the value of alpha. If the value of alpha is less than or equal to alpha 0, then instead of taking this value, or for that matter any value below it, I take f0. The error I'm making is at most 10% the error, or 10% the actual value of f that I should be using. So this is the exact expression. Instead, I use the limiting expression, and as long as alpha is less than that limiting value, the error I'm making is at most 10%. Okay? So now the value of alpha 0 will depend on eventually where this intersection occurs. I know the value of f0. In this case, it's 1. In this case, it's 1.12. And then I calculate that value. In this case, it's simply 1.1. In this case, it is equal to, just give me a second, and I can calculate it for you. It is 1.12 times 10%. It is 1.232. So in this case, if f is 1.232, I can go ahead and find the corresponding value of alpha 0 from this green line. That green line depends on the case that I'm looking at. I'm going to give you an example shortly for the exact form of f. I go ahead and do this check, and if this check works, then I can use the blue equation instead of the red equation with 10% accuracy. So the value of alpha 0 depends on the green line, which depends on the case I'm looking at. It turns out the value of alpha 0 for this scenario is equal to 0.4. So that's alpha 0. In this case, it is equal to 0.6. And in this case, it is equal to 0.13. Okay? So when we go back to this particular case, for instance, and if I were to pull on this plate, right, it is this scenario, and you can see that the width of this crack is not less than 0.13 times the width of the plate. So the assumption is violated, okay? And probably, therefore, not probably, but certainly, this expression is not valid to within 10% accuracy because the value of alpha for this particular case is not here. It is all the way perhaps there, and the value of f should be, let's say, that, and that value is much larger than the 10% error bound on the value of f. Okay, so instead of that case, I should be using this case. So to summarize, people have agreed upon a so-called 10% accuracy limit on f and therefore on ki. Let us remember it to be on ki. Okay, so with 10% accuracy on ki, if this assumption, this is satisfied, you can use this approximate expression, which is very simple. If it's not satisfied, you certainly need to use the red equation. You can always use the red equation, irrespective of whether the 10% limit is satisfied or not. That would be working with the exact green line all the time. However, it turns out that the blue expression, when possible, is a lot simpler to make use of compared to the red exact general expression. We're going to see why with an example on our next slide. Okay, or the slide after that. So this is always true. Okay, this is true if you can ensure that 10% accuracy limit is satisfied. Okay, so now we have discussed these scenarios, and therefore now this 10% limit, to elaborate further, if this is satisfied, K1 is not exactly equal to SG root pi A, it is approximately equal to SG root pi A. K1 is equal to this if A is much, much less than B, or alpha is much, much less than 1. If it's not satisfied, Ki is not equal to this quantity, it's only approximately equal to it, to within 10% accuracy, provided that this limit on alpha is satisfied. Now, likewise, if A is not much, much less, if it is, this is exact. If not, this is not exact. You have to go ahead and, just like every other case, go and use this general always true expression. But if alpha is less than 0.13, this expression is still true to within 10% accuracy. And I hope all of the stuff that I have written on the same slide will keep you informed about what is going on. If I expose everything to you at once, perhaps it's complicated, but if, because we're building step by step, I hope everything is clear. So that's the picture that we are looking at. The final thing that I would like to comment on is the form of f. As I said, this is the exact expression. It's true for every loading scenario, every crack geometry, etc. And for that matter, the plate geometry or the structure geometry in general. But the value of f, the form of f, depends on the case we are looking at. The form of f for this particular scenario is something that I'd like to give as an example. Here, the form of f is given as 1 minus 0.5 alpha plus 0.326 alpha squared divided by 1 minus alpha square root. Okay? That form of f of the form factor is special to this case. In general, every case will have its own functional form that we have to make use of. Those are tabulated in your book, so that's where you can have a look at it. Here we can easily check that this curve is meaningful. If alpha is equal to 0, this is 1, 0, 0, f is equal to 1. Right? It starts from 1, f0 is 1 indeed, right? Here there's like a factor 1, f is 1. And if alpha keeps growing to 1, this thing blows up to infinity. Okay? And now, just as a fun scenario, what we can do is we can go ahead and plug in alpha equals 0.4, which is alpha 0, into this expression. So let's do that actually together. Okay? So I'm going to, first of all, 1 minus 0.4 square root. Let's do that again. 1 minus 0.4 square root. This is that value. Inverse. Let's keep that in memory. 1.29 approximately. And then I'll calculate that function. 1 minus 0.5 times 0.4 plus 0.326 times 0.4 squared. And then I will multiply it with this value, 1 over that value that I just calculated. So what I'm doing is I'm calculating the value of f at alpha 0. Okay? Remember, alpha 0 is the 10% limit on K1 and hence f. So what should we have when I hit the equality sign? It's 1.1, right? Because that's the 10% limit on f. If alpha is 0, f is 1, then 10% limit is 1.1, right? So it's exactly as it should be. All right. So now this is the case that we have looked at, and what we've considered is the generalization from our ideal geometry by saying that, well, perhaps the width of the crack is actually not that small, and also perhaps the geometry of the crack is not actually the same in every case. Okay? And what we've done is we've generalized the expression for determining K1. The criterion is always the same, but the expression is slightly generalized by incorporating a form factor, and now this is an expression that is always true. Now let us take one final step and look at slightly different types of loading, which are still mode 1 type loading, where I try to open the crack. So not every opening mode has to do with tensile loading, right? Or it doesn't have to do with a uniaxial load. It can also be a bending type loading. Okay. So the question is, what if loading is different? And for that scenario, I am going to consider a plate again, the same plate that we have looked at. And let's draw it twice actually. And I will introduce a edge crack. Okay, so the definition of the width of the plate is B. The half width of the crack in this case, or the whole width, is A, but it's like half of a edge crack scenario, if you like, with two cracks. So when I split through the middle, the width is half, the crack width is also half. So that's the way we denote it. That's the convention. We don't have to memorize this, except the ideal or prototypical scenario. We don't have to remember anything. We just have to know how to use the tables and understand the meaning of the equations. Okay, so the thickness is T in this case as well. Okay, well, now if I pull on this thing, right, it's gonna be the scenario that we have already considered, but we're not going to pull on it. Instead, we are going to either bend it, or I'm going to load it in a way that is similar to bending. Now, if I bend it in a way that I, like this scenario, if I bend it so that I will try to close the crack, I know nothing happens. If I try to open the crack, if I try to bend it like this, then fracture is important. So bending is only relevant in that direction. Okay, so in the other direction, we don't need to consider fracture. So in this case, I'm going to say, or I'm going to use a loading scenario that is statically equivalent at the cross section where the crack is at least, statically equivalent to bending. And that is the type of loading that we are going to consider. Okay, so the definition for the height, let us put that in. Let's call this H. We can assume that H is much, much larger than B presently. And now we would like to consider or analyze fracture in this scenario. So first of all, what is the criterion that we need to employ? Now, in both cases, I have a bending type scenario, and in both cases, due to bending, the crack faces will try to move away from each other, right? I try to bend in this case as well, so that's an opening mode. So I'm looking at K1. And the criterion is always to take K1 and compare it against the fracture toughness, K1C. Okay, that's our failure criterion. And what is always valid is that K1 is equal to some form factor times the gross stress multiplying root by A. And the expression for SG is now also the expression that I have written in the previous slide in green. SG is, remember, is equal to the maximum stress at the location where the crack is present. Okay, so at the cross section where the crack is present, the maximum stress at that cross section, omitting the presence of the crack. So I'm looking at that cross section. Okay, so that cross section is like this, this portion of that cross section is actually a crack, but I omit its presence, so it's like this blue rectangle that I'm looking at. The plate is bent, and I would like to calculate the maximum stress at that cross section, but omitting the presence of the crack. So this is a simple loading scenario, and the stress, the maximum stress at the blue cross section is simply delivered through MC over I. And let us that's our equation that we remember from ME 231, mechanics of materials. Well, what is the value of C? Well, the value of C, we're bending, right? Let me turn this picture again. It's MC over I. So it would be, this would be our, if you like, neutral axis, right? And the distance, the maximum distance from the neutral axis, so the maximum tensile stress occurs here. The distance is half the width, which is B over 2. So C is equal to B over 2, and I is equal to 1 over 12. The whole height, which in this case is equal to B cubed times the thickness. 1 over 12, the thickness times the height to the cube. Okay, and therefore the expression for SG is equal to, if I simplify through, it is 6m over B squared T. Now, that's for a given explicit bending moment. Well, in this case, what is the bending moment? Well, at that cross section, the statically equivalent loading imposes a bending moment of P over 2 multiplied by this distance, which is H. Okay, so in both cases, at the cross section where the crack is present, there is a bending moment of M, and SG is defined as the gross stress is the maximum stress at the location, at the cross section where the crack is present, but omitting the presence of the crack. So the value of I, or C for that matter, is not reduced by the area reduction due to the crack. I omit the crack altogether. So it's just a simple mechanics of materials calculation. So it's MC over I, C is B over 2 in both cases, and I is 1 over 12 B cubed T. So I know that I have to apply that expression, and if I know the value, the form of F for any given value of alpha, alpha is equal to A over B in that case and in that case as well. And I can take that, plug into the form of F, and I can take that value, plug it in there. For the given bending moment, I know SG, I know the crack size, I know the value of F, I can calculate K1 and decide if there's fracture or not. Okay? Now, but I can use an approximate expression, F of alpha 0, I know that it is 10% different than the value of F at alpha equals 0. So Ki in that case is approximately equal to F of alpha 0 SG root pi A 10% error if alpha is less than or equal to alpha 0. So this expression is always true. But if alpha satisfies the 10% limit, then with 10% error on K1, I can use a slightly slightly simpler expression, which I am sorry now I'm correcting. This should be 0. I can simply use the value of F at alpha equals 0, which in this case so for these cases that I am considering, F of 0 is, unlike our prototypical case and like the two other cases we have considered in the previous slide, it's equal to 1.12. It's not 1. So the limiting case omits f and instead puts not 1, but 1.12, but because this geometry is special, has a special consideration, and that's the correct value of the limiting value of f. Okay? So now we've said a lot, we've written a lot. Now I think it's a good time to go ahead and apply these expressions and ideas to an example.